So I have some problem-solving strategies, okay? And then let's look at some examples of just setting some things up here. So it says here, step 1, identify 2 states to the system, where one state is known and the other is an unknown state. That is, one state you know everything about. That means you know its speed, you know its height, you know its spring compression. And the other state, you only are missing a little bit of the information. Maybe you don't know the speed, maybe you don't know the height, maybe you don't know the compression. But the goal is always to determine some type of position or some type of speed. Then for each state, identify the associated kinetic and potential energies of those points, and then apply conservation of mechanical energy and solve for the appropriate problem. So let's go look at some simple examples and apply this. So here we go. So as examples, let's talk about the first one here. Let's say that we drop a perfect ball onto the floor. Maybe I don't have to say perfect, but let's do this 2 ways. So now what we're going to do here is that I imagine that I have a table right here. And then I'm going to drop a ball right here. I'm going to drop my ball. And all I know is that what we're going to do is that when we drop it, eventually it's got to do what? It's got to come all the way down to here. So what actually happens here? So here's what I see here. I'm going to isolate the system. Okay, I'm going to come in here and I'm going to isolate the system. Now that I isolate the system, I says, what are the forces acting on this ball? Are there any external forces or are there any forces? And one of them, there is the force of gravity. Now, if I drop this ball onto the floor, we typically assume no air drag. And so are there any other forces? And so that means here in my system, it's really the ball plus Earth, because I have to include the force of gravity. Is there a spring force? No. Is there any other force? The answer is no. So because work external is 0, that means it's a force. It's the only forces I can consider are the spring force and the force of gravity. Then that means that the total mechanical energy is now the same, which then tells me that the energy before must be the same as the energy afterwards. So I know mechanical energy is conserved. So then I start to look at the details. What do I know? Let's say that when I look at state 1, I'm going to call this state 1, and I'm going to call this state 2. So what is known about state 1? Well, even though I didn't mention it, let's say that we do know what the height of 1 is. And we're going to say that this height y2 will set it equal to 0. So what we can say here is that, let's say that the ball starts at rest from height y1. So when I look at the total energy of the system, I could then say that the total energy of the system is then going to be K1 plus UG1. But if it's starting from rest, we immediately know that that guy is 0 because it's starting from rest. So when I look at my bar system, it's telling me that I have this amount of potential energy. My energy 1 is completely gravitational potential energy. And since I can't create or destroy energy, this energy is a fixed quantity. It is a constant no matter what. So then I want to know what's happening at state 2. So at state 2, I could then come over here. Let me move this over here. So then I could ask the question, what do we know about state 2? Well, its height is 0, which then tells me that its gravitational potential there is 0, but we do not know its speed. So then what we're seeing here is that at this state, state 1 is a known energy. State 2 is an unknown energy. In other words, conservation of mechanical energy says that I know everything about energy 1, but I don't know everything about energy 2. It's an unknown. So when I look at this thing, I could then come over here and just say, when I get to the bottom here, I see that the gravitational potential energy is 0. Here, we see that the kinetic energy at 1 is 0. So then we are forced to conclude that all of the potential energy has transformed into kinetic energy. So then, this is my bar diagram. My bar diagram then says, if I look at these energies, it says that I have K1 plus UG1. That's going to equal K2 plus UG2. From the bar diagram, we can clearly show that that is 0 because it starts at rest. This is 0 because it's at the ground. So now I can rewrite this as mgy1 equals 1/2 mv2 squared. So right away, this now gives me an equation that this allows me to solve for V2. So conservation of energy is setting this stuff up here. Let's look at a different situation. Let's look at one more example, and it goes something like this. And this will, what we're going to have here is that we're going to have a cart bouncing. I guess I should say bouncing off a spring. Okay. So we want to set this up so that we don't add friction to the situation, because I'm not going to give you a friction problem on the exam. So my picture then looks something like this. So I'm going to imagine that I have a frictionless surface with a cart colliding with a spring. How much compression occurs? So picture-wise, I imagine that we have a frictionless surface, and at this end, I have a spring. And the only thing that I know here is that I'm going to have a cart coming in. So it's essentially a sliding block. We can't talk about rolling. So this cart is coming in. And what I'm going to say here is that we expect that if I know the initial speed, let's say that this guy comes in with some speed 1. Okay, so this is a known quantity here. So now I ask about my system here. So when I look at my system right here, note that, are there any forces acting on this thing? And the answer is, yeah, there is a force of gravity, but there's also a normal force. So that tells me that when I look at the net force acting on the system, that net force is going to be 0. Because I have equal and opposite forces. So I'm going to get, let's say, normal minus mg, that's going to be 0. So those forces, they do not change the energy. The only time we care about this is when I have this situation. We don't care about out there. We care about what happens when there's a collision. We only care just before and after the collision. So then if I redraw this thing here, here's my system here. What I really need here is that I need this block to be right here. That's what we care about. So when I look at this, this is the before. And then afterwards, what happens? The spring has now compressed. And so I can see that during this process, a compression has occurred. So now if I look at my system here, what is my system? So my system here, I'm seeing that I do have a force, and this is the force of the spring. Gravity and the normal are not going to contribute to this. So now we know that the spring force will take all its work and convert it into spring potential energy. So now this is what I have afterwards. And so afterwards, if we want maximum compression, that means that its final speed should be 0. So then I start drawing my picture. So what does my picture says here? It says that I have a total energy. And this total energy, because the only force is friction here, this total energy has to be a constant. And so when I look at this thing, right before it collides, there's no spring interaction. So right before, all of this energy has to be in the form of kinetic energy, where the spring potential energy at 1 is 0. So if this is the case, then I don't have to worry about what happens afterwards. I don't care how this thing is compressing. All I know is that in the end, if I look at just the endpoints, I know that at K2, it stops it. It gets maximum compression. So then this tells me that the rest of this is only spring potential energy at 2 here. That's my equation right there. That is completely my equation. So when I look at this thing, note that I didn't include gravity, so I don't have to worry about gravity. But then I start to look at this thing and it says, what is the energy before? What is the energy afterwards? And then we start to go, okay, I have this amount of kinetic energy. I have this amount of spring potential energy. And then afterwards, I have that amount of kinetic and I have that amount of spring. So when I start to look at these guys have to be identical, but there was really no contact with the spring. And here, this we brought to a rest. So then conservation of energy tells me that it has to be like this. So then I could then come in here and write that this is 1/2 mv1 squared plus 0. That's going to equal to 0 plus 1/2 kx2 squared. So again, what you're seeing here is that we have now set up an equation. So we set up an equation to solve for x2. So conservation of energy is giving me that ability to do that here.